Okay, so it's a little introduction to lab exercise 4, parallel interface, input, output, and control. So we're going to use several of the ideas introduced in chapter 4 in this lab exercise. So PWM, optical encoding for determining the position and velocity of the motor, finite state machine, control algorithm, instruction timing to produce a calibrated delay. You're even going to be doing capturing data, looking at data on an oscilloscope. You guys have arrived, okay? It's all happening. It's all happening this week. Buttons on little little breadboards. It's great. So this exercise, your program will control and monitor the speed of a DC motor. The interface between the myRIO and the motor will be digital input-output channels and an FPGA encoder counter. See figure 4.9. So let's take a look at this figure. So what we're going to do, so the myRIO's over here, and we're going to take a digital output from the myRIO and put it into an analog amplifier, current source amplifier. And you might think, well, why the hell would we do that? It's a digital output going into an analog amplifier. That was the end. I didn't have an explanation. There's no. It's to give you guys an opportunity to use the digital outputs in a finite state machine. It's not the recommended way. I'll tell you at the end of this. Like, if you want to use PWM, to use this other PWM method, we're going to do it. We're going to sort of roll our own poorly just to get a lot of experience doing it. It's kind of fun. So we're going to use the analog amplifier. We're going to just do PWM, like we're going to sort of roll our own PWM on this, which totally works. It's just not how you would usually use an analog amplifier. An analog amplifier that can switch on and off quickly, which this one can. You can run PWM through it. It'll happily amplify that for you, and you're good to go. But usually, you would just use an analog output to this, and later we will use an analog output to this amplifier. For now, we're just going to do a PWM one because we're actually going to build the PWM with a finite state machine. It's kind of fun to build a PWM signal. So we'll do that, and that output's going to go into the DC motor, which will turn this motor, and you get to see things move. Super fun. It's a very gratifying moment when you hit that code and it's like deploying to the myRIO, and it starts running, and then it says enter speed, and you enter in a speed, and you hit enter, and the motor starts to turn. You guys should all look forward to that moment, okay? It's really great. So we are then going to keep track of the position of the motor, and what we'll be adjusting in our case is we'll be looking at the speed. We'll be actually measuring what the speed is. We're not going to do closed loop control, though. We're not going to do any control on it. We're simply going to set it to some voltage, some duty cycle. It's going to supply power, and it's going to turn that motor, and we're going to measure what the speed of the motor is. And we're not going to change it at all. It's just going to be that, okay? Later we'll do closed loop control on it, but you got to get all the parts before you can start doing the whole loop. So we are essentially going to do some PWM into this amplifier, turn the motor, measure the position, deduce the speed from the position, and we'll also have these two buttons that we're going to interact with. So there's going to be a button that's for stop and a button that's for print. Okay, the stop button is going to, you guessed it, stop the motor and the program execution. Okay, the print button we'll talk a little bit about the print button is effectively going to be what's going to tell us to print the speed, the measured speed, on the screen. So as it's running, it won't typically be printing the speed, but when you hit the print button, you hold the print button down, it should be printing the speed to the LCD screen, and then when you let it go, it should stop. So that's kind of the operation that we're running with here. So this sort of goes through the details of how we're doing PWM. So this bar over everything is because the logic is essentially reversed. So this is the not run channel. So when this is high, we're not running. When it's low, we're running. Okay? So it's the opposite logic, so it's the not run channel. This is the not stop. Okay? And then this is the not print. So the logic is essentially reversed, so that instead of being the print, stop, and run channels, they're the not print channel, the not stop, and the not run. And yeah, go ahead.
So the amplifier circuit, you're going to build it, right?
This is all built for you. So we don't have to build the amplifier circuit. The only circuit you're going to have to do is effectively connecting up the buttons to the connectors and the MyRio. Yeah, so not too bad. I think you guys can handle that one. Later we'll do some nice digital logic circuits, which will be fun. You guys will love that. Not this week though. So this week we've got a lot of things to take care of. So initializing the encoder in FPGA. So show you how to do that. Talk about reading the encoder values, which is actually incredibly straightforward. Then you're going to have to build this operation for a finite state machine. So you're going to have its 4 different states. High, which means that you're going to be, so not run will be 1, and then low is going to be not run equals 0. So this is going to be low on not run is essentially meaning apply voltage. Okay, so when not run is 0, it means run. Okay, when not run is 1, it means actually don't run. Okay, because we're very intelligent and we can do double negatives. We're not limited by the doubleness of the negativity. So this is what we've got. Essentially, this thing's going to run where it's going to be applying the pulse during the low state for a certain number of counts. Then it's going to go to the high state for a certain number of counts based on whatever we're going to have the user set N and M. And then we're going to just go back and forth, low state, high state, low state, high state, until somebody hits the print button. And when the print button is hit, when you transition from run equals 1 from the high state, you're going to transition to the speed state for 1 count, which is to print. For 1 count, you're going to be printing to the LCD screen what the speed is that you're measuring. And then you're going to go to the low state, and then you're going to go back to the high state, and then the speed state, low state, and then until the person releases the button, in which case you go back to this. Okay, so you're going to go back and forth. Effectively, you're going to go between low and high, low and high. Sometimes you're going to have to go low, high to speed to low to high to speed to low to high. And then when somebody hits the stop button, then you go to the stop state. So that's pretty much what you do. And then this gives you a lot of details. And it tells you about all the different functions. Essentially, you're going to have to write these functions for each of these states, right? The low state, the high state, the speed state, which is what happens when we hit the print button, etc. So this gives you a lot of stuff. It has the wait function in there again. And there's this thing where you have to actually determine how long that wait is going to be by looking in the manual of the processor to find out how many cycles each of these opcodes takes, and pay attention to the branch instructions, which are going to be like the loops, right? So that's going to be fun too. You can get to do that. You can get to look at the oscilloscope because there is a whole procedure here that happens, laboratory procedure, where you're going to have these buttons. You're going to have to make some observations, look at the waveform on the oscilloscope, measure how much time things are actually taking, compare that to the amount of time that you said it was going to take, and recording a step response. You're going to have to do this too. And in here, you're going to actually be exporting data from C to MATLAB. Okay? All this is explained in painstaking detail in here. So look forward to that. It's actually, none of it's too bad, and I mostly give you all the code to do the MATLAB export stuff. So you don't have to write your own stuff for that. Yeah. Okay, any questions on that? Oh, and then at the end I say, if you want to do PWM with this thing, not using a finite state machine in the very ineffective way that we're doing it here, then you use, there's actually a PWM little library that is that you can use. So that's the recommended way. We're doing PWM here just to do a finite state machine and do different process control, which is fun. So it's a fun lab. Okay, questions? All right, move to adjourn. Do I hear a motion? Okay, all in favor? Aye. Opposed? Abstentions? Okay, motion carries. We're adjourned.